Hello and welcome to this video on what's going to be in the 2022 exams. This video is for the AQA specification and it's for combined scientists, and the trilogy version of combined science is what we're looking at. And that's for combined scientists that do 6 exams at the end, all of which are 1 hour and 15 minutes long. So this video is going to focus on chemistry paper 1 and is for higher tier students. So do check with your teacher if you're not sure if this is the right video for you or not. But if you study combined science or are a higher tier student, then this will be the video for you. And this is looking at chemistry paper 1. First of all, the exam board tells us what topics won't be assessed in the paper, but unfortunately for chemistry paper 1, there is nothing off the table. So they could assess you on anything you've learnt in the topics. So you do need to look over everything for your revision. However, later on we'll tell you the topics that you need to focus on in particular. The required practicals they've asked us to focus on are salts, electrolysis, and endo and exothermic reactions. And whilst these will appear in this video, the place to go will be the required practicals video, and I'll put the link for that in the descriptions. So if you want to have a revision session just based on the required practicals, which will cover 15% of the exam, then I would have a look at that video. So the topics we've been asked to focus on in the exam are how bonding and structure are related to the properties of substances, use of amount of substances in relation to masses of pure substances, so these are calculations, reactivity of metals, reactions of acids, and electrolysis, and finally exothermic and endothermic reactions. So the rest of this video is going to be on these major foci here, and as I said before, if you want the required practicals on their own, head to the link in the description. States of matter quite simply means whether something is in a solid, a liquid, or a gas state. This is a topic that also comes up in physics, topic 3 as well. So if you learn this bit for chemistry, that'll also help you for physics as well, and vice versa. So here we've got the 3 different models that we can use. So this one represents a solid, this one represents a liquid, and this one a gas. And it's showing how the particles are arranged depending on whether the substance is in solid state, a liquid state, or a gas state. Within chemistry, we also write these as state symbols in chemical equations. So you can see here we've got solid, liquid, and gas, and the final one here, the AQ, means it's aqueous, which is in solution, okay, or dissolved. So AQ stands for aqueous. So for a solid, if you're asked to describe the arrangement of particles, we need to be talking about the fact that they are in fixed positions. The particles are vibrating, which you can't see by this diagram, but they are vibrating. The particles in the solid form a definite shape and volume, and there are strong forces between the particles. For a liquid, the particles are close, but they move over each other. They're moving randomly. Liquids don't have any definite shape. So for example, if you had a container and you were to pour the liquid in the container, it would just take the shape of the bottom of that container. There are weak forces between the particles, which allows them to move over each other. With a gas, the particles are far apart. The particles are moving randomly in all directions. A gas has no definite shape, and in fact this will fill and take the shape of any container that you put them in. So if you were to put a gas into this container, it would completely fill the container and take the full shape of the container. And there are very weak forces between the particles, weak intermolecular forces, and they can move past each other and be far apart. Higher tier pupils will need to be able to write about the limitations of the model. So that just means what limits there are to drawing particles in this way as a solid, liquid or a gas. So what the examiner is looking for is the idea that particles aren't really spherical. Particles will come in all different shapes and sizes depending on what they are. So for example, if you had a water molecule that was H2O, that wouldn't be spherical, that might occupy this kind of shape instead. However, in these diagrams, we always draw them as spheres. The particles aren't solid either, yet we still draw them as solid spheres. And these diagrams here don't show the forces between the particles. So that's from our own knowledge. We don't see from these diagrams that these have strong forces between the particles, that these have weaker forces, and these have very weak forces between the particles because they are not shown. Substances can change state between solid, liquids and gases depending on whether energy is gained or lost by the particles. So the change of state between a solid and a liquid is called melting. If you were to heat the substance up further from a liquid to a gas, that change of state is called boiling. On the other side, you can cool the substance down, and if you cool the gas, you can condense it to form a liquid, and if you cool a liquid down far enough, you can freeze it into a solid. Now the melting point and the freezing point happen at the same temperature, depends whether you're heating it up or cooling it down. And the boiling point and the condensing point happen at exactly the same temperature. For example, if the boiling point of a substance was 1083 degrees C, for example, then that would be the condensing point of the substance as well. If the melting point was, say, 400 degrees C, then that would also be the freezing point. It all depends whether you're heating the substance up or cooling it down, depending on which change of state you would be cooling it. So if you're on this side, you are gaining energy. So the particles are gaining energy to move from a solid to a liquid or a liquid to a gas, and the particles are moving more. They're already moving or already vibrating in terms of the solid, so we're talking about them moving more. And by moving more, they are overcoming the bonds that are holding them in place. So, for example, if we remember our solid model, we've got particles that are vibrating with strong bonds holding the particles together. But if those particles gain energy, they are going to vibrate more, and then they are going to overcome these strong bonds that are holding them in place until they turn into a liquid where they can move over each other and have weaker forces of attraction between the particles. If a substance is being cooled down, it is going to be losing energy to the surroundings, and therefore they don't have enough energy this time to overcome the forces of attraction. And as they lose energy and then therefore can't overcome these forces, you will end up with bonds forming between the particles as it changes state. So here we're going to get more stronger bonds forming between the particles to make it a liquid, and even stronger bonds forming between the particles to turn it into a solid. Perhaps the most difficult thing with changes of state that you might be asked to do is interpret tables giving information on melting and boiling points, for example. You need to remember that melting point is exactly the same as freezing point, and boiling point is exactly the same as condensing point in terms of the temperature that they occur at. So, for example, if they said what is the state of oxygen at minus 100 degrees C, perhaps the easiest way to do it might be to write out the solid, liquids and gas and realise that from the table oxygen melts at minus 218, so that would be its melting point and also its freezing point, so we can write those in, and it boils at minus 183 degrees C, and that means it would also condense at minus 183 degrees C. So if the number is lower than the minus 218, that would be a solid. If the number here falls between minus 218.4 and minus 183, that would mean it would be a liquid. But as minus 100 is smaller than minus 183, it falls in this side, so oxygen would be a gas. For carbon, it says what is the state of carbon at 3600. Again, I'd go to write my solid, liquid and gas for carbon, and we can see that the melting point is 3500, so is the freezing point, and the boiling point is 4827, and so is the condensing point. So where does 3600 fall? Well, it falls between these two numbers here. 3600 falls between these two numbers, so that means that the carbon must be a liquid at 3600 degrees. So with the positive and negative ions that we've just discussed, these can attract each other and bond together, and this is exactly what we mean by ionic bonding. So ionic bonding is between a metal and a non-metal, and we said that metals are the ions that have a positive charge and non-metals have a negative charge, and they attract with each other. For example, this could be sodium, Na+, and this could be chlorine, Cl-, and when these react together, they will make a compound called sodium chloride. Now, to write the formula, we need to look at the charges, because that is a single plus and that is a single minus. We just need one of each and put them together like so, NaCl. However, if this ion here was magnesium, magnesium is in group 2, so it has a charge of 2+. If we're bonding that with chlorine, we can't just put them both together because this is 2+ and 1-. So we'd need 2 chloride ions to balance out the charge of the magnesium. So we'd need to write MgCl2. Similarly, if you had sodium bonding with oxygen, because oxygen is 2-, this time you'd need 2 sodiums, so you'd write Na2O. So this is how you'd write the formula of the ionic compounds. Now they all have a very similar structure, and it looks something like this in this picture just here. Because it's not just the case that one ion will bond with another ion and they will go round together. They actually form a giant structure. So you can see here there's a big lattice of positive and negative ions all in one big structure. So we call it a giant structure. We call it a lattice. If they ask about structure, you need to talk about the fact that it's made out of positive and negative ions. And keeping those ions together, they're shown together by a bond in this diagram, but we call those forces electrostatic forces because they're charged particles, they're charged ions. It's electrostatic forces act in all directions to keep that structure together. Check very carefully in the exam whether they're actually asking you about properties or structure or both, because properties are a bit different. Properties are talking about melting points and boiling points, for example. These ionic compounds have high melting points and high boiling points. They don't conduct electricity when they are a solid, but they will conduct electricity when they are molten, and I'll explain why in just a sec. So they only conduct electricity when molten, which means when they're melted down into a liquid. For example, in this case here, you've got positive and negative ions throughout. However, they are fixed, they cannot move. Electricity is the flow of charge, or current is the flow of charge, but at the moment in this solid state here, these ions cannot flow. However, if you make them molten, you then have a situation where you've got your sodium, for example, and chloride ions in there, but they are now free to flow. This is important for electricity. And if these ions are free to flow, that means charge, because the ions are charged, is moving around. A second type of bonding is covalent bonding. And covalent bonding is between non-metals. So you could have two of the same element. For example, here you've got chlorine. Or you can have two different non-metals bonding together. For example, methane. You can see from these diagrams that these particles aren't charged and instead they're sharing electrons. So there's no transfer of electrons this time. Instead, they just bond together by this really strong bond because they're sharing electrons. We can draw this in other ways. We can draw the covalent bond simply as a straight line to show a covalent bond. So we can do that for both of them. And you may well see diagrams in this format. These lines show a covalent bond, or you can draw it without the energy shell, so you can just draw the electrons like so. And you may see it without the circles, and you can do the same for methane. But this is the covalent bond here, where they're sharing electrons. So chlorine is in group 7. You can say each individual chlorine atom has 7 electrons. So this one has 7 crosses, and this one has 7 dots to represent the electrons. And because they both need 1 electron, instead they will share a pair of electrons. And if you look at each individual atom now, they will have 8. So 1, 2, 3, 4, 5, 6, 7, 8. And this one, 1, 2, 3, 4, 5, 6, 7, 8 by that share pair. Here, in the same way, hydrogen only ever had 1 electron and carbon has 4 electrons. So you can see just by sharing the electrons here, hydrogen is now complete because it has 2 electrons in its shell, and that is full because it only has the inner shell. And if we look at if we look at the carbon atom, that has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, giving that a complete shell. So you may well have to complete diagrams to show covalent bonding. A little tip is to think about how many electrons they need to complete their outer shell, and that will know how many pairs of electrons the atoms will need to share. So oxygen is in group 6. If it's in group 6, that means each atom has 6 electrons on the outer shell, and they need 2 more. So because they need 2, that's your hint that this is going to have this time 2 shared pairs of electrons. So I'd start there. So draw 1 atom with dots and 1 atom with crosses to make it nice and clear. So we start with our 2 pairs of shared electrons in the middle. And now we know that we've used 2 electrons up for each atom. And because they started with 6, they can only have 4 more. So if I make this one the one with dots, I will put 4 more electrons, doesn't matter where you put them, around the outside. This one here, I will put 4 crosses around the outside. So in total, if we look at this oxygen atom here, it only has its 1, 2, 3, 4, 5, 6 crosses that it started with. However, in total, it now has 8 electrons because it's sharing some with the other oxygen atom. and this one, it only has the 6 that it started off with, but again, if you look at it, it has 8 electrons because it now has this double covalent bond. So we would draw a double covalent bond with 2 lines, like so, to show the oxygen atoms bonding together. Nitrogen then is in group 5, so this needs 3 extra electrons for a complete shell, so that's where we start. We start with 3 shared pairs of electrons. And this time it will only have 2 more on the outer shell like that. So if we look at this nitrogen atom, it has 5 crosses because it was in group 5, but now as a complete atom here it has 8 because of these electrons here. You've got 6 here, 7, 8, and the same for this one. So this is now a triple covalent bond, which we would draw with nitrogen with 3 covalent bonds, to another nitrogen atom. So the structure and properties of covalent molecules are very different to ionic bonding that we looked at before. They don't form giant structures anymore. You will literally see the oxygen molecule going around as one molecule, O2, and the nitrogen going around as N2. They don't form giant structures. So they are simple, small molecules. They are joined together by strong covalent bonds. And they have weak intermolecular forces between the molecules. What that means is the covalent bonds between the atoms, so here this double covalent bond is very strong. It's very difficult to split these oxygen atoms apart. However, if you had 2 oxygen molecules close together, they have what we call intermolecular forces, so forces between the molecules, and these are very weak. So the bond here is very strong and the bond here is very strong, but these intermolecular forces which exist between the molecules are very weak. And having weak intermolecular forces means that they have particular properties, including this time a low boiling point and melting point. So many of these simple small molecules are gas at room temperature. Not all of them, but many are gas at room temp. And also, because these particles are not charged in any way, they do not conduct electricity. Next, we're going to look at giant covalent structures. And in the next section, I go into detail about graphite and diamond, but this is unlikely to come up in the higher tier paper as it wasn't listed as a major focus. So you do need to know that giant covalent structures are solids with very high melting points and that all of the atoms are linked with strong covalent bonds. And you do need to recognise what diamond, graphite and silicon dioxide look like, but the in-depth information about structure and properties of graphite and diamond are unlikely to come up, but it's worth just brushing over these just in case they do appear. In rare cases, covalent bonding can also lead to giant structures, and there's 3 giant covalent structures in particular that you need to be aware of, and these are diamond, graphite, and silicon dioxide, or you may well see that written as silica. So with these giant covalent structures, they still have very strong covalent bonds. They are giant structures, lattice structures, and this gives them very particular properties. Unlike the small simple molecules, these giant covalent molecules actually have very high melting and boiling points. and as a rule they generally don't conduct electricity. Except graphite, and we'll explain why that does so in just a sec. So a little bit more detail for diamond and graphite that you need to be aware of. Let's go into the elements first of all. You can see these are just made from one type of element. These are both made out of carbon, whereas silicon dioxide is made out of silicon and oxygen. So with the carbon structures here, we can describe these as allotropes of carbon. This means they are different structural forms of the same element. So these are both made out of carbon, but they're very structurally different, and therefore they have slightly different properties to each other. With diamond, each carbon makes 4 covalent bonds with other carbon atoms. So carbon's in group 4, it has 4 electrons in its outer shell, and it makes 4 strong covalent bonds. It uses all the electrons that it has. However, with graphite, it only makes 3 covalent bonds with each of its carbons. Therefore, it has a spare electron on each of its carbon atoms, which is delocalized. It's allowed to move throughout the structure. This delocalized electron gives it a very particular property in that it can conduct electricity. So graphite only makes 3 carbon bonds with each of its carbon, therefore it has a delocalized electron, and therefore it's free to move throughout the structure and it can conduct electricity. Because diamond has 4 bonds, it is a very strong structure, and it is a very hard material, one of the hardest materials on our planet. Graphite, however, forms layers, and you can talk about that when you're talking about the structure. It has weak forces of attraction between the layers, and that means the layers can slide quite easily, and it is quite soft. Graphite is the substance used in pencils, so as you use a pencil, you're literally taking layers of graphite from the inside of your pencil. With graphite, if you took off just a single layer from the top, we call that graphene. So a single layer of graphite is called graphene, and that is very, very light because it's just a single layer, but it's still a very strong structure because of these covalent bonds. So graphene is something that's being used in new technologies to strengthen materials without adding much weight. A final molecule that involves covalent bonds are polymers. You can see here, we said before that straight lines between non-metals represent covalent bonds. So you can see this polymer is made through covalent bonding. But with this polymer, you can see that we've only drawn a small section of it, and this is the repeating unit that repeats again and again and again. So if we draw it as a square, that would be joined to another one and another one and another one and so on until we got a really, really long chain polymer. Hence this N here, that just means any number. So this can be any number of units long. If we were to write this out, which you might be asked to do in the exam, the formula for the polymer, you need to count up the number of carbons. So there's 3, so C3. Count up the number of H's, there's 3, 4, 5, 6, so 6 hydrogens. And you would write that in brackets with the N outside, and that would be our formula for the polymer. Most polymers then are solid at room temperature. And whereas we said with the simple molecules that there were weak intermolecular forces, With polymers, if we had two polymer strands, for example, like here, the forces between the molecules, the intermolecular forces, are a lot larger. And that therefore gives them a much higher melting point and boiling point than simple molecules. Hence why a lot of them are solid at room temperature compared to a gas, but they're still got much lower than something like an ionic bond or a covalently bonded structure. So larger intermolecular forces between the polymers, giving them a higher melting point and boiling point. The final type of bonding that you need to be aware of is metallic bonding, and that's the bonding that exists between metal atoms. For example, if you were to pick up a large lump of gold, there would be metallic bonding between the gold atoms to make sure that that structure stays together. And this model here shows what metallic bonding looks like. It's represented by the positive metal ions. And with metals, the outer electrons are actually free to move around. So we say that they are surrounded by what we describe as a sea of delocalized electrons. So if we were to draw electrons in here, we'd have the positive ions there, and the electrons would be moving all around the structure. And that gives it a very particular property that we know about with metals, in that they are very good conductors of heat and electricity. They also have very high melting and boiling points. You should know this because you can appreciate the amount of energy that it would take to heat and melt a metal. So you should remember that they have high melting and boiling points, and you should already know that most of them are solid at room temperature. General properties of metals then, they are also very strong and malleable, meaning they can be bent and hammered into shape. That's what malleable means. So when you're asked about the structure in the exam, you need to be talking about this part, the sea of delocalized electrons and the positive metal ions in a regular structure, the fact that it forms a giant structure, and the properties, conductors of heat, electricity, the melting and boiling points, and the fact they are strong and malleable. So with metals, there's two different types that we use regularly. There are pure metals. The thing with pure metals, though, is they're actually quite soft because the metal atoms or the metal ions are arranged in layers, and those layers can slide over each other easily. Meaning that you can move the atoms around, you can shape the object, and it's quite soft. However, to make metals a lot harder, we can make them into an alloy, and an alloy is a mixture of metals. So you can see here that you've got different sized metal atoms. And this means that the layers are now distorted, so the atoms are not in regular layers. And what that means is the atoms can't slide over it easily in an alloy. So this structure makes them a lot harder, and this is a really common question in the exam. So either they'll ask you about the pure metals and simply you need to write about the atoms being in layers and being able to slide easily, or they'll show you a diagram of an alloy, or maybe ask you to draw a diagram of an alloy, and we need the fact that it's now got different sized atoms, distorted layers, or the atoms aren't in regular layers, and the fact that the atoms now can't slide easily over each other, and it makes a much harder substance. Here are the three equations for the higher tier paper that I recommend you write down and learn off by heart. And then when you get into the exam, you can brain dump them, which means write them down straight away on the first bit of white paper that you see, so you don't forget them. Moles in chemistry is a word to describe a particular number of particles, and that number of particles comes from Avogadro's constant, which is a very particular number of particles, 6.02 times 10 to the 23 particles. So 1 mole of a substance will contain 6.02 times 10 to the 23. It's just like using the word dozen to represent 12. We would say we have a dozen toy cars, for example, rather than saying we have 12 cars. Well, rather than saying we have 6.02 times 10 to the 23 atoms of carbon, we shorten that by saying we have 1 mole of carbon. The mole is represented by the large numbers in front of chemicals in an equation. For example, this equation here we can write out in terms of moles, and you may be asked to do this in the exam. So here we would describe this as 2 moles of hydrochloric acid reacting with 1 mole of calcium carbonate to produce 1 mole of calcium chloride, 1 mole of water, and 1 mole of carbon dioxide. So this is what the large number is representing, the ratio of moles that you have in the equation. Moles relate to relative formula mass in an equation that we'll talk about on the next slide. However, quite simply, the relative formula mass in grams is how much 1 mole weighs. For example, the relative formula mass of calcium carbonate from the previous slide we worked out as 100. So it has a relative formula mass of 100. So 1 mole of calcium carbonate would equal 100 grams. Whereas water, we said, has a relative formula mass of 18. So 1 mole of water would weigh 18 grams. Or if we talk about it in terms of the number of particles, we're saying 1 mole, so 6.02 times 10 to the 23 particles of calcium carbonate would weigh 100 grams, or 1 mole, which is 6.02 times 10 to the 23 particles of water, would weigh 18 grams. This equation here is one that you're definitely going to have to remember, and I would highly recommend you writing that down as soon as you get started in your exam. Just turn over the first page and then a piece of blank space, write down moles equals mass divided by mR, because it's likely that you will need that in your exam. So questions such as this: how many moles are there in 16 grams of carbon dioxide? Well, if moles equals mass divided by mR, we would need to work out the relative formula mass of carbon dioxide. Using our periodic table, the mass of carbon is 12 and the mass of oxygen is 16. So 16 times 2, because there are 2 oxygen atoms in there, will give you a relative formula mass of 44. So how many moles are there? Well, moles equals mass divided by mR, so 16 divided by 44 would give you the answer of 0.36 moles. Second question, how many moles are there in 2 grams of calcium carbonate? Well, the relative formula mass of calcium carbonate, if you were to work that out, is 100, because we've got 40 added to 12 added to 3 lots of 16. So moles equals 2 divided by 100, which would give the answer of 0.02 moles. Concentration is mass over volume. Now, concentration is measured in grams per decimeters cubed. That means the mass must be in grams and the volume must be in decimeters cubed. What they'll do is sometimes trick you out by giving you the mass in kilograms, okay, in which you need to, because it's kilo, times 10 to the 3, or times by 1,000 to get it into grams. And the volume, they give it to you in centimeters cubed. Get yourself an easy mark. If you see centimeters cubed, divide it by 1,000 to turn it into decimeters cubed. So let's look at this one. It says, what's the concentration of a sodium chloride solution made from 2 grams, that's the mass, of sodium chloride dissolved in, there's your banana skin, 200 centimeters cubed of water. They're trying to make you slip up. So that's the volume, but we need to divide that by 1,000 to turn it into decimeters cubed. So we get 0.2 decimeters cubed. So that gives us 1 mark, and we then put our numbers in the equation. So the concentration is what we want. So concentration equals mass 2 divided by volume 0.2, which gives us an answer of 10 grams per decimeters cubed. Now, you may be asked to rearrange it as well. So if you notice that they're asking you to calculate mass or volume, you're going to have to rearrange it. Same as before, but this time you also have the equation concentration equals moles over volume. So this question says, what's the concentration of sodium chloride solution made from 0.4 moles of sodium chloride dissolved in banana skin, 500 centimeters cubed of water? Banana skin, because it's wanting you to divide by 1,000. This will be your first mark to give you 0.5 decimeters cubed. So then moles over volume would give you 0.4 over 0.5, which is 0.8 moles per decimeters cubed. Now, if you're wanting moles per decimeters cubed, but then you need your answer in grams per decimeters cubed, the decimeters cubed bit is staying the same. So you need to think how you convert moles to grams. So then you use the equation moles equals mass over mR. So moles would equal the mass over mR. So if we want to get from moles to mass, we would need to multiply by the relative formula mass. Okay, rearrange that, mass equals moles times mR. So we'd have 0.8 from before multiplied by the relative formula mass of sodium chloride, which they've given you here, to give you 46.8 grams per decimeters cubed. So this is a case where they've asked you, look at the units carefully, for grams per decimeters cubed and not moles per decimeters cubed. Could be 4 marks or so for that question. I want to run through balancing equations using masses. For these ones, you get the marks for the working out and not for just balancing equations. So they give you masses and they give you relative atomic masses. So think to yourself straight away, moles equals mass over mR. So 19.5 is the mass. I've just written out again here. If you take the question and write it out as an equation, it will help you. So then we divide by the relative atomic mass. So for just K, it will just be 39 because there's only one thing. 9 grams here. H2O would be 2 lots of H plus 1 lot of O, which is 18. K plus O plus H would be 56 for a relative formula mass, and then H2 is 2. If you do that, you will get a ratio of 0.5 to 0.5 to 0.5 to 0.25. So we're nearly there to balancing our equation, but it can't have decimals in. So if you divide everything by the smallest one, that will give us a ratio of 2 to 2 to 2 to 1. And the final thing, don't miss out this step, is you have to write the balanced equation. So for this one, you get marks for your working out and not for simply writing this final answer at the end. So you'll know if you got it right, if the equation balances properly, but this is where you get your marks using the moles equation. because this equation is showing us the ratio of moles that are reacting 2 to 2 to 2 to 1. Let's calculate the mass of sodium chloride produced when 2 tons of sodium carbonate reacts with hydrochloric acid. So we want 2 tons. I always write it under here, it just helps me out. So 2 tons of sodium carbonate reacting with hydrochloric acid, and how much sodium chloride do we need to make? What we need to find out could well be on this side of the equation as well, it doesn't matter. But everything else, just put a cross through because you don't need to worry about that. So I recommend you doing the moles mass MR in a grid for each thing. So moles mass MR in a grid, moles mass MR. So write down the information that you know. Now, really, you should convert these to grams, but I'm just going to keep it as the tons because it will work out the same in the end. So I'm going to put down here 2 tons for the mass of sodium carbonate that I've got. And then using my periodic table, I would need to work out the relative formula mass. Again, they might give you those numbers, but I'll tell you now that the relative formula mass of this is 106. The relative formula mass of sodium chloride, don't include the 2, okay? Ignore that because we'll use that later. Think to yourself, I'll use that later, so I'll ignore that, is 58.5. So the one thing that I can work out, that's everything that I've got first of all. The one thing I can work out is this bit, the moles. So moles equals mass over MR. So 2 divided by 106 will give us 0.01887. This is where these numbers come important, the ratio of moles. The ratio of moles here is 1 sodium carbonate to 2 sodium chloride. So when we convert the moles over here, we need to double up because we've got a ratio of 1 to 2. So doubling this will give us 0.0377 moles. And then we rearrange our formula, moles equals mass over MR. If we rearrange that to MR times moles equals mass, we know to multiply these two together to get our answer of 2.2 tons. Now you could have done it in grams and then converted it back into tons. That's fine as well. Now I would recommend converting these ones to grams first of all, because in last year you were Dr. Mark if you didn't do a limiting reactant question in grams. So first of all, I would recommend you converting these. Don't forget kilo is times 10 to the 3, so it's timesing it by 1,000. So you'd have 20,000 and you'd have 50,000. So it's saying when you react these two together, ignoring this side, when you react these two things together, one is a limiting reactant. That will mean that it will all be used up, and the other one you add in excess. Okay, so the limiting reactant is the one that's used up. First of all, we'll talk about neutralization, and the general equation for neutralization is when an acid reacts with a base to make a salt plus water. Now this base can either be insoluble, so something like calcium oxide where you'd have a powder that you'd add to your acid, or it can be soluble, something like sodium hydroxide, where you would have a liquid or a solution that you react with the acid. And soluble bases have another very special name called alkali. So if you see an alkali reacting with an acid, you know that that is a soluble base or a solution that you're using. When you react an alkali with an acid, you can use an indicator like universal indicator, or a piece of equipment like a pH probe instead, which is an electrical piece of equipment that will give you an exact number, because the universal indicator links with the pH scale. So this here is the pH scale. It goes from 1 to 14. Number 7 in the middle, pH 7, is for a neutral substance, for example, water. So sometimes you have a pH 0 as well on the end here. The range 0 to 6 are your acids, so the range 0 to 6. And within the range 8 to 14 are your alkalis, 8 to 14. Now acids are solutions that have hydrogen ions in them, whereas alkalis have the ion hydroxide in them. So I'll just write that hydroxide out. Hydroxide ions for an alkali and hydrogen ions for an acid. Now with the neutralization reaction, you're taking an acid and you're reacting it with a base to make a salt plus water. So if you're making an acid with hydrogen ions, react with an alkali with hydroxide ions, you can see that the result of those two reacting are going to make water. And also you'll make a salt in the reaction as well. But this is the Ionic equation for neutralization. So using the pH scale, we can describe acids that are far away from neutral as strong acids, and the ones that are closer as weaker acids. In the same way with alkalis, the closer you are to water and to neutrality, the weaker you are, and the further away you are, there's your strong alkalis at the end. This section on strong and weak acids is for higher tier pupils only. This section on strong and weak acids links again to the pH scale. So just in a little bit more detail, pH is a measure of the concentration of hydrogen ions in a solution. So we said before that here with our 0, our 1, these are our strong acids, and here are our weak acids. When you go down a number on the pH scale, you increase the number of hydrogen ions in your solution by a factor of 10. So that's something to be aware of. They might give you a certain number of hydrogen ions that are in a pH 6 solution and perhaps ask you how many would be in a pH 2 solution. You have to keep multiplying by 10 until you get to the right pH. So they increase by a factor of each 10 as the pH decreases. But the words strong and weak acids also refer to particular types of acid. Strong ones are the ones that you are probably used to using in your lab. So for example, hydrochloric acid, sulfuric acid and nitric acid. Note that they all start with H because they're all producing hydrogen ions. When they dissolve in solution, strong acids completely ionize in water. What ionizing means in this case is they completely break down into their two ions. For example, hydrochloric acid would completely ionize into H+ ions and chloride ions when it is dissolved in water. Whereas weak acids are things such as citric acid, carboxylic acids like ethanoic acid. And with these weak acids, they only partially ionize in water. Partially ionizing means that if you have, for example, ethanoic acid, which is CH3COOH, when that breaks down in water, it's actually a reversible reaction. You do get hydrogen ions and the negative part of the ion as well, CH3COO-, so it does break down and form hydrogen ions, but because it's reversible, these form again to produce ethanoic acid. So you get fewer hydrogen ions in solution. So in this case, you get more hydrogen ions, whereas with a weak acid, you get fewer hydrogen ions. And this will, of course, relate then to their pH on the pH scale. The more hydrogen ions that you've got, the stronger the acid, the fewer hydrogen ions, the weaker the acid. So this makes these strong acids more reactive as well, because there are more hydrogen ions in there that can then react. But also we can look at them in terms of the difference between strength and concentration, because we could have two bottles of acid with the same concentration, hydrochloric and ethanoic acid, and we can both, for example, have the concentration of 1 molar. They've got the same amount in grams dissolved per volume. Remember those units from concentration. So they've got the same amount of acid dissolved in solution. However, because this one will be completely ionising in water, producing lots of hydrogen ions, this will be a stronger acid with a lower pH, whereas this ethanoic acid here will only partially ionise in water, so it will be a weaker acid with a higher pH. There are several chemical reactions that you need to know of as part of this topic. First one that we'll look at is reactions with metals and water. So when metals react with water, they will produce a metal hydroxide and hydrogen gas. So potassium and water would make potassium hydroxide plus hydrogen. If you remember from when we looked at the periodic table, potassium will actually float on top of the water and perhaps will spark and flame as well, because it's a reactive group 1 alkali metal. But this will work with any metal that will be able to react with water. So for example, you might have magnesium reacting with water, and this time you'll produce magnesium hydroxide plus hydrogen. Some metals are not reactive enough to react with water, like copper, so you wouldn't be able to write an equation for that, but anything that reacts with water you can. For the next reactions, many of them will produce something called a salt. So let's talk about how we name salts first of all. We name salts in two parts. They will have one part that is the metal that's in the salt, and the second part will depend on the acid. So there's 3 acids that you need to know about in particular. Sulfuric acid makes a sulfate salt. Nitric acid makes a nitrate salt. And hydrochloric acid makes a chloride salt. Okay, so those 3 we really need to remember, because then we'll be able to name all of the salts in this exam. So this is an example of our first reaction that's going to produce a salt plus hydrogen. So if you put a metal in with an acid, you'll produce a salt plus hydrogen. Naming the salts then, we've got the metal iron, and this time we're reacting with hydrochloric acid. So following our rules, we'll make iron chloride plus hydrogen. Here we've got iron and sulfuric acid reacting, so we make iron sulfate this time, plus hydrogen. And finally we've got nitric acid this time, so we'd make iron nitrate plus hydrogen. If we change the metal, for example, if this was magnesium, instead we'd make magnesium chloride and hydrogen, and so on. In this reaction, we are reacting acid with a metal oxide this time. So before we were just reacting it with a metal and producing hydrogen. Now we've got oxygen in there, we're producing water instead. So we're producing a salt plus water. So nitric acid and sodium oxide, there's the metal, sodium, and we used and we're using nitric acid, so we're going to make the salt sodium nitrate, and our second product is going to be water. It's very, very similar, and we've got a metal hydroxide here. So whereas this was sodium oxide, which is Na2O, this time we've got a metal hydroxide, which in this case is iron hydroxide, which is FeOH2. So it's the OH hydroxide we've got now, but same way it produces a salt plus water. So this time the metal is iron and we're using sulfuric acid, so we make iron sulfate plus water. In this reaction we've got now a metal carbonate, and if you see the word carbon you must think to yourself that this reaction also produces carbon dioxide. So you've got hydrochloric acid plus zinc carbonate, and you're going to produce a salt plus water plus carbon dioxide. So let's name the salt first of all. The metal is zinc and the acid is hydrochloric. So we will make zinc chloride, and then we will make water, and because it's a carbonate we will also make carbon dioxide. Two further reactions, we've got oxidation and reduction. In terms of a chemical reaction, oxidation means the gain of oxygen, and reduction means the loss of oxygen. You also see these two words later on in terms of electrons, and they mean something different, but for the moment we're talking about a chemical reaction. So in this one, zinc reacts with oxygen, and zinc gains oxygen, so it forms zinc oxide. And in terms of reduction this time, it means the loss of oxygen. So this time, zinc oxide would lose its oxygen, so you'd make zinc plus carbon dioxide. We'll now talk about the required practical, which is all about making a salt. So to make a salt, we're going to do a neutralization reaction. So we've got our base reacting with our acid to make a salt plus water. In this case, we've got copper oxide reacting with hydrochloric acid to produce copper chloride salt and water. You could use sulfuric acid to make copper sulfate. It all depends on what salt that you want to make at the end of the process. So this copper oxide, you can see by the state symbol, is solid, it's insoluble, and it is a black powder. That will react with acid and make a soluble salt. You can tell by this state symbol of AQ, which means aqueous, that is soluble and it's going to be dissolved in water. So to start off with, to make our salt, we need to add the copper oxide in excess to the acid. Really important term, it means we keep adding it until no more reacts. So we have our acid in our beaker, certain amount, say 30 mils that we would measure with our measuring cylinder, and then we keep adding that copper oxide in excess until we see the copper oxide at the bottom of the beaker to show that no more can react. We now need to get rid of that, because if we were just to heat that, we wouldn't end up with our pure crystals, we'd end up with some copper oxide on top as well. So the first process is filtration. We'd pour that reaction into our filter paper with inside our funnel. And in the conical flask, we would collect our solution containing our salt and our water, and at the top here we would have our excess copper oxide collected and filtered out. The next process is to then get rid of the water, because we just want the salt on its own. So the next process is called crystallization, and you can either use a Bunsen burner to heat up an evaporating dish over a tripod. Sometimes you might choose to heat it up more slowly in a water bath, or using an electric heater. You might see any of those heating methods in the exam, but we put our solution into there and our water will evaporate. And that will leave us, after a while, we might take it off the heat and leave it to finish evaporating off the heat, but we will end up with crystals left in our evaporating dish where we've actually extracted our salt crystals. So you need to be able to describe this method and say each step by step what you need to do to create your soluble salt. You may see in the exam that to help the insoluble base react with the acid, you may see this acid heated over a Bunsen, just gently, just to warm it up a little bit before this is added. But obviously that's going to have safety precautions associated with it because you're heating acid and you don't want that spitting out of the beaker. Also here, when you're heating the crystals, this must be very gentle heat, otherwise they can end up drying out too quickly and spitting at you as well. Now we're going to look at the reactivity series. The reactivity series is how we list metals in order of their reactivity. So here we've got potassium, which is most reactive, and then copper, which is least reactive. Copper is really useful because it doesn't react with many things. It doesn't react with water, so you can use it as water pipes and things like that. Also, not on this list, but you'll find substances such as gold. They're completely unreactive, which we'll talk about later when we're talking about extracting metals. Within that list as well, you'll also have two non-metals. You'll have carbon and hydrogen that you need to be aware of. Again, important for metal extraction a little bit later on. You may well be asked to have a look at some examples of experiments and work out the order of reactivity. For example, if we had some potassium in this conical flask over here, this would react with water quite vigorously. In fact, potassium would float on top of the water because it's got a low density from group 1, and it would react vigorously, perhaps producing a flame as well, and fizzing around on top of the water, producing lots of hydrogen gas. That would show that that was really reactive. You might then have something like magnesium, which you would put in another conical flask. Again, that would fizz quite a lot, producing a fair amount of gas, but not as much as the potassium. And then finally, you might have something like iron. That would give fewer bubbles of gas and would obviously be less reactive. So you might have to have a look at descriptions of experiments and then work out their order of reactivity. Linking into the reactivity series then, we're going to talk about how we can extract metals by the process of reduction, which is a chemical reaction we talked about earlier, which involves removing oxygen. So here we've got the reactivity series again, and this is important to understand what methods we can use to extract metals. Now, apart from metals such as gold, which are completely unreactive and can be found naturally, you can sieve for gold in the river and it won't have reacted with anything else, it's just found in its natural state. All the other ones tend to react with things like oxygen and form a rock, which we call an ore. So this is a rock which contains metals. For example, this rock could be iron oxide. But when coming to extract metals, we need to take that iron oxide and actually take the iron out of that rock. And there might be other impurities in there as well. There may well be sulfur and carbon in the rock and things like that. Now, with iron, as well as zinc and copper, one way we can do this is by a process of reduction. And this can only happen with anything that is below carbon on the reactivity series. So we can't do reduction with potassium, sodium, lithium, calcium or magnesium because they themselves are more reactive than carbon. This is an example. Let's use iron as an example. If we have our ore, which is iron oxide, and we want to extract the iron, we would heat it up with carbon, and that would then produce iron and carbon dioxide, which is the reduction reaction that we looked at when we looked at chemical reactions. It's called reduction because you are removing the oxygen from the ore. If you were to do this with magnesium oxide, nothing would happen because the carbon is not reactive enough to take away that oxygen. So this only happens for metals that are less reactive than carbon. So for example here, you might see in the exam them talk about a blast furnace where they may do this kind of reduction reaction. So in here they would put your iron oxide and your carbon, and you'd need hot air going in here, and out at the bottom you'd end up with your molten iron, and any impurities also come out of the bottom. It's a substance called slag which comes out the bottom, and any of your waste gases will come out the top, so your carbon dioxide and so on will come out the top. Redox reactions is a topic for higher tier pupils only. Again, it involves the two words oxidation, meaning the loss of electrons, and reduction, meaning the gain of electrons. And what you need to be able to do is understand in a formula like this where you have atoms and where you have ions. If the element is on its own, that is an atom. If it's bonded in a compound with a non-metal, that makes the metal an ion. So copper is an ion there, whereas iron is an atom. Iron here is an ion, whereas copper is an atom. So in this case we've got iron that is turned from an atom to an ion, where it would go into Fe2+, and we've got copper which is turned from an ion, Cu2+, to an atom, which is just Cu. So in this case the iron atom would have lost electrons, and therefore that would have been oxidized, because oxidation is the loss of electron, and the copper would have gained electrons to turn back into a copper atom, and therefore the copper would have been reduced. So they might say to you which species, meaning which chemical in a chemistry sense, has been reduced, or which species has been oxidized in this equation. And you need to look at which ones are turning from atoms to ions and which ones are turning from ions to atoms. These equations are called redox because you have something that is being reduced and something that is being oxidized in the same reaction. Ionic equations are for higher tier pupils only. So when you see a neutralization reaction like this, you can actually write it as a simpler ionic equation, which only involves the elements that are changing from ions into atoms or vice versa. So in this equation above, because it's a neutralization reaction and it's producing water, one trick to remember is when it's neutralization, the ionic equation is always going to be the same. Hydrogen reacting with hydroxide ions to produce water. Everything else are spectator ions. For example, to show you here, the chloride ion here is still a chloride ion on this side of the equation. That hasn't changed. The sodium ion here is still a sodium ion on this side of the equation. So they're both spectator ions that can be taken out. However, you've got here a hydrogen ion and a hydroxide ion that then bonds together as a molecule of water. So what we're doing is getting rid of the ions that are staying the same and writing out in its simpler form to show the ions that are changing and reacting. So the ionic equation for any neutralization reaction is going to be the same. Hydrogen ions plus hydroxide makes water. You can also write ionic equations for displacement reactions and other reactions in the topic. But let's have a look at displacement. We'll look at the elements that are changing between ions and atoms. So in this case, we've got a magnesium atom, and now it's bonded, it's now an ion, so that's going to be changing. We've got a zinc ion, which is changing into a zinc atom, but the chloride ions are staying the same. They're bonded this side, they're an ion, they're bonded that side. So they're spectator ions that can be removed, and we can write an ionic equation which shows magnesium atoms react with zinc ions. Zinc is Zn2+, and they will produce magnesium ions, Mg2+, and zinc. And one more example here, you've got iron atoms that turn into ions and copper ions that turn into atoms. The sulfate ion we don't need to worry about because it's a spectator ion, it stays an ion both sides. So our ionic equation getting rid of the spectator ions would be iron atoms add copper ions producing iron ions and copper atoms. Another process in which you can extract metals is called electrolysis. Electrolysis uses electricity to split up compounds. So electrolysis uses electricity to split metal compounds. But the trouble is with electrolysis is it uses a lot of energy because of the electricity needed, and therefore it is very expensive. So with the metals that are below carbon in the reactivity series, really you want to be using reduction because that's cheaper. However, some metals such as aluminium, you can't use reduction because they're more reactive than carbon, so you would have to use electrolysis, and it makes it a little bit more expensive. Let's take our basic example first of all, and this links back to ionic bonding. So with our ore, let's say for example here we had lead bromide. Remember back from ionic bonding, we've got a metal and a non-metal bonding together. So this comprises of ions. We've got our lead ion, Pb2+, and two bromide ions, Br-, bonded together to make that compound. Now, if we were to stick two electrodes in there and link it up to a direct current supply, nothing would happen. Because in this state here, whilst it's solid, if you remember from ionic bonding, we've got a lattice structure of positive and negative ions throughout, but the trouble is these ions can't move anywhere. But you can make this molten by heating it up, and when you do that, when you make it molten, those ions are then free to flow. So the bromide ions and the lead ions can then move around and conduct electricity because they are moving charges. This is not talking about electrons flowing in this liquid here. We are talking about ions that are free to flow. So please don't write electrons. Make sure you're talking about ions. This liquid here is called the electrolyte. And these are the two electrodes. You've got a positive electrode, otherwise known as the anode. But if you don't remember that, just write positive electrode. And the negative electrode, which is the cathode. And this, as I'll show you later, is connected up to a DC supply. So in this simple case here, we've got our ore and we've heated it up so it is now molten and the ions are free to flow. Within here we've got positive ions, they will be attracted to the negative electrode, and here we would have lead collecting around the negative electrode, and to the positive electrode you will have the bromide ions going, and they will go off as bromine, which is Br2, and you'll see the bromine gas given off at the electrode. In a second case here, I'm going to talk about the electrolysis of aluminium oxide. Aluminium oxide has an extremely high melting point, which would make this process very expensive. So what they do first of all is they dissolve it in something called cryolite, and that then lowers the melting point. So it takes less energy to heat it up and melt it and make it molten, which in turn saves money and makes the aluminium cheaper. So in here we have a mixture of, well, in this complete chamber, in fact, we have a mixture of aluminium oxide and cryolite. That's our electrolyte. Aluminium oxide and cryolite. And this time, you need to look at the diagram very carefully, and they'll show you on the diagram. But this time they have 3 positive electrodes at the top. There may be 4, there may be 5, there may be 6, there may be more than that, doesn't matter on the number, but all of the ones going in at the top are now positive electrodes, and actually the negative electrode is the outside casing. So in here we have aluminium ions, Al3+, and oxide ions, 2-. The aluminium ions are positive, so they are attracted to the outside, and then they are tapped off at the bottom. So here you get molten aluminium coming out of the bottom, which you will then collect and use for whatever you want. At the top here you can see the positive electrodes, and this is where the oxygen is attracted to. So you get oxygen given off. But also what happens is, there's a really common question in the exam, these electrodes are made out of graphite. And if you remember, graphite is made up of one element, and that is carbon. So they often ask, why do these graphite electrodes gradually degrade and wear away? And the answer is, the oxygen that goes to these electrodes reacts with the carbon, producing carbon dioxide. So these gradually degrade because the oxygen reacts with the carbon to produce carbon dioxide. So in this electrolysis you will also get carbon dioxide given off as the oxygen reacts with the electrodes, and then they gradually need to be replaced over time. There is also a required practical on electrolysis, so be prepared to describe a method to set up electrolysis and also predict the results of the electrolysis. So for this we're going to be talking about electrolysis of aqueous solutions. That's when they are dissolved in water. So not only will you get a particular ionic compound, but you will also get the ions that are found in water. So you need to be able to draw a setup from scratch. So you would need to draw a container and show electrodes going into that container connected to a power supply. When you draw the power supply, the long line of the cell would be the positive, connected to the positive electrode, and the shorter line to the negative electrode. And then you need to show your electrolyte solution covering the electrodes. And you can label those up. So you'd label the electrolyte, which is the liquid that you're using, your electrodes, so your positive electrode or your anode, your negative electrode, and your DC supply. It has to be direct current, otherwise it won't work. So let's say for this example, we are doing the electrolysis of sodium chloride solution. So with sodium chloride, if you were to split that up, you would have two ions, sodium and chlorine. But because it's in solution, it also means that you have the ions that are in water. So you would also have hydrogen ions and also hydroxide ions in that solution. And that poses a problem because you have negative ions, two of them, and two positive ions. So that means that you need to predict what is going to go to the negative electrode and what is going to go to the positive electrode. So in this case, the rule at the negative electrode is the least reactive element goes to the electrode. So in this case, hydrogen is less reactive than sodium, so you're going to get hydrogen gas given off. And with the positive electrode, if there is a halide ion in there, then that will be produced at the positive electrode. If not, oxygen will be produced. So in this case, we've got our chlorine present, so chlorine will be produced, Cl2. If a halide ion, remembering that halide is a halogen from group 7, so if halide ion is present, that will go to the electrode. If not, oxygen is produced because it's to do with the hydroxide ion going to that electrode instead. So if not, oxygen is produced. And I'll show you an example of that in just a sec. So you might need to draw this out, show the ions in there, and predict what is going to be produced. So we've got a hydrogen gas produced. We can test for that using a squeaky pop test. Comes up in paper 2. Chlorine produced. Again, these tests come up in paper 2, but you may see them as well. And to test for that, you would bleaches a damp litmus paper. So you would put blue litmus paper in and it would turn from blue to white. Left in solution then you have a positive ion and a negative ion, so these are going to attract together and produce sodium hydroxide in the electrolyte that is left. So an example then of when oxygen might be produced, again if we had our chamber set up and we had our positive and our negative electrode connected to our power supply. This time, for example, if we had copper sulfate, we would have copper ions in there, sulfate ions, and the ions that are present in water because it's copper sulfate solution. The same rule applies to the negative electrode in that the least reactive element goes to the electrode. So in this case, the two positive ones are copper and hydrogen. And out of those two, copper is less reactive, so copper will collect at that electrode. And for the positive electrode, you've got hydroxide and sulfate ions. As we don't have a halide ion present, we don't have a group 7 ion present, then our rule says that oxygen will be produced. So at this electrode, you will get oxygen given off because the hydroxide goes there and produces oxygen, which is given off, and water, which goes back into the solution. Half equations is a topic for higher tier pupils only. Half equations can relate to electrolysis, and it all relates to the two words oxidation and reduction, but this time in terms of electrons. So oil rig will help you remember that oxidation is loss of electrons, and reduction is gain of electrons. Now this is different to the chemical reaction that we looked at earlier, which is in terms of gaining oxygen and losing oxygen. So this is definitely in terms of electrons. If you lose electrons, you're oxidized. If you gain electrons, you're reduced. So let's look at lead bromide again, where we got Pb2 plus and Br minus in solution. We said that lead would go to the negative electrode and bromine would be produced at the positive electrode. So you need to be able to write half equations for these, which basically just shows what's happening in terms of electrons. So lead ions, when they go to the negative electrode, they gain electrons and turn into lead atoms. So that is the half equation for what is happening at this electrode. And because they're gaining electrons, reduction is happening at the negative electrode. Lead ions are turning into lead atoms. So with bromine, bromide ions lose electrons and they turn into the bromine molecule. So bromine goes around in pairs, so it must be Br2. So we need to balance that up by a 2 there and a 2 there. The other way that you can write this around for the half equation for bromine, you may see it the other way by saying that bromide ions turn into bromine atoms and lose 2 electrons. So for the positive electrode, there's 2 ways that you can write the half equation. Other examples, for example, hydrogen. The hydrogen ions were to go to a negative electrode, there they would gain electrons and turn into hydrogen molecules, which we'd need to balance up. And chlorine, for example, if chloride ions lost electrons, they would turn into chlorine, and again we'd need to balance that. We'll start off by talking about exothermic and endothermic reactions. Exothermic reactions give out heat to the environment or the surroundings as we call it. So exo, like exit, you're going out, so that might help you remember that exo means give out heat to the surroundings. And there's several different reactions. Most reactions are exothermic, so things like neutralization reactions when you add an acid to a base. Respiration is an exothermic reaction. Energy is released during respiration, so it's an exothermic reaction. Metals and acids. Anything that gets hot shows that the energy is being released to the surroundings. These have several practical uses as well, for example in things such as hand warmers or self-heating cans, where you can initiate a chemical reaction and heat up food. Endothermic reactions are the opposite. These reactions take in heat from the surroundings. So endo means take in heat, whereas we said exo means give out heat. Typical reactions that are endothermic are things like thermal decomposition reactions. Looking at their name, they use heat, thermal, to decompose or break things down. So they need to take in heat to break down particular chemicals. Photosynthesis, which is the opposite of respiration, is an example of an endothermic reaction. And practical uses are things like sports injury packs. So in here you will have an endothermic reaction which you can initiate and then put on an injury, and you can imagine if you've hurt your knee or your leg, there's going to be lots of heat from that injury which can be taken in by the endothermic reaction, which will then cool down your injury and help it feel better. These diagrams show reaction profiles which show the overall energy transfer in chemical reactions. You have 2 lines on these. You have the reactants and the products. If you remember, all the chemicals on the left-hand side of an equation are the reactants, and they produce products. So in this reaction, in these reaction profiles, you just have to say what you see. You've got the progress of the reaction and energy. So in this case, the energy of the reactants is lower than the energy of the products. This means energy must have been put into the reaction because the products have more energy. So this reaction profile shows an endothermic reaction, whereas with this one, again, say what you see, the reactants have more energy than the products. So energy must have been given out, so this is an exothermic reaction. When you're asked to explain why it's exothermic, you can say that the reactants are higher than the products, so they have more energy than the products, and the opposite way around for this one. So there's a couple of key points. You need to label these very carefully. If you're asked to label the activation energy, make sure you are doing so from the reactants up to the product, to the top of the products, and the same for this one here. This I'll label A, but it's the activation energy. This is the minimum amount of energy needed for a reaction to happen. And this comes up in paper 2 when you're talking about collision theory as well. So A is the activation energy, and the other thing that you might have to label is the overall energy change, which I'll just call delta H, because that's what we normally call it, overall energy change. And that's the difference between the reactants and the products. So here, this is the overall energy change, and the energy is going up. And in this case here, you need to make it as exact as you can. This is the overall energy change, and the energy is going down. So in this case, the delta H is negative, and this case, the delta H, or the change in energy, is positive. The only other thing that you might be asked to do is show the effect of a catalyst on these diagrams. A catalyst provides an alternative pathway with a lower activation energy. It tends to come up in paper 2, that definition, but here we can show an alternative pathway with a lower activation energy. So it's got to be lower than the activation energy here, and in the same way on this side to show the catalyst. Now we'll discuss a required practical on exothermic and endothermic reactions. So with this practical, you'll be asked to investigate the temperature change of a reaction, and you might be asked to change a particular variable such as concentration or mass of the reactant and see what effect that has. The main thing with this practical is the reaction happens in a polystyrene cup, and you'll have a thermometer in there to see how the temperature changes in the reaction. But the main thing that they'll ask you is how to improve the apparatus in the equipment. The main things they'll miss off are a lid on the cup. Okay, so we must have a lid here, and also a lid on the beaker would be preferable, with the cup surrounded by some form of insulation. So they're the main improvements that you need to look for. Has it got insulation? Has it got a lid to prevent heat loss? Or in terms of endothermic, heat actually going into the practical. So for example, if you wanted to look at an exothermic reaction, you could either do a neutralization reaction, or you could, for example, put a metal in with an acid, and when you do that you'll see a temperature rise, and you can measure that on the thermometer. You might want to change the concentration of the acid, for example, maybe use 0.1 molar, 0.2 molar, etc., maybe up to 1 molar, and then you could see the effect that that has on the temperature change in the reaction. You could also do an endothermic reaction if you wanted to. For example, you could have water and something like potassium chloride. You could put those both into the cup, and you could measure the temperature decrease this time in the reaction. And for potassium chloride, you might want to change the mass that you're using. So maybe start with 5 grams and then use 10 grams, 15 grams, etc. and see the effect that that has on the temperature change. So bear in mind that you might be asked for improvements for this investigation, or you might be able to you might be asked to write a method from scratch for a particular reaction. If you're doing a neutralization reaction, for example, maybe you're reacting hydrochloric acid with sodium hydroxide, for example. If you're using these two liquids, you must make sure that they start at the same temperature. So you might want to put those in a water bath, say at 25 degrees C before the reaction, and then you know that they both have the same starting temperature, and that means that temperature is therefore controlled before the reaction begins. Bond energy calculations are for higher tier only, and what you need to remember for these calculations is that energy is released when bonds are made, and energy is needed or taken in when bonds are broken. So the second line is more easy to understand. So to break bonds between atoms, you need to put energy in, so energy is taken in, that makes sense. And this other one is the opposite effect of that, which is slightly harder to get your heads around. But whenever a bond is actually made, energy is released. So we can calculate the overall energy change in a reaction. In an exam, you'll be given the equation. Make sure it is balanced. Normally they will balance it for you. They will give you the displayed formulas for the chemicals in the equation, and they will give you a table that shows the bond energies. Now these are constants. You can look these up on the internet and you will be given these in exams. So for example, the energy needed to break a CH bond is 413 kilojoules per mole. Alternatively, this would be the energy released when that bond is made, depending on whether you're making the bond or breaking the bond. So with bond energies, you need to add up all of the energies, all of the bond energies on the left-hand side, and then all of the bond energies on the right-hand side. So in this case, they've given you the displayed formulas, and they will do in the exam. So you need to make sure you circle all of the bonds and add all of them up. So here we have 4 CH bonds. So CH has a bond energy of 413. So we have 4 lots of 413. And we add that to 2 O double bond O bonds, which have bond energy of 498. So 2 times 498. And on this side, again, make sure you circle all the bonds so that you don't miss any out. You've got C double bond O, C double bond O. So that's 799. So 2 lots of 799. Added to 1, 2, 3, 4 OH bonds. So 4 lots of 4, 6, 3. And be really careful. You notice when I was writing, I nearly made a mistake there. You need to copy these numbers carefully from the table, otherwise you'll lose all of the marks. So if we add that up on the left hand side, we've got a total bond energies of 2648, and on the right hand side a total of 3450. That will get you a couple of marks. Your final steps you need to do is take 3450 from 2648, so do this number minus that number, and that gives you an answer of minus 802 kilojoules per mole. And that number there is the overall energy change in the reaction. And because it's negative, it gives you the clue that that is an exothermic reaction. If you remember back from the reaction profiles that we looked at, that means the reactants have more energy than the products. So the overall energy change here, delta H, is negative, hence that negative value there of minus 802 kilojoules per mole. So when you do this last calculation, it may well be a negative number or it might be positive.